In this work, we investigate 6 different bimanual interaction techniques varying the level of interaction fidelity realism to teach basic metrology concepts used in the engineering industry. A large-scale experiment was conducted to identify broader trends in performance and learning outcomes and how they were affected by the different levels on a continuum. The simulation was created such that the same dependent variables could be measured across all conditions for analysis. The camera view for low-fidelity conditions was a top-down view of the workbench looking into the screen. This was not true for the medium and high-fidelity conditions. The camera view for these conditions was such that the workbench was out in front of the user. Since low and medium fidelity conditions use a large screen display, there was a visual motor mismatch on account of the virtual end effectors not being co-located with the physical hands. The low-fidelity 3 degrees of freedom condition was based on the dimensional symmetry aspect of McMahon's FIFA framework. It was determined that simplifying the interaction by reducing the number of degrees of freedom could potentially aid user interaction. The 3-DOF condition allowed for 2 positional axes about X and Y and 1 rotational axis about the Z axis. The low-fidelity 6-DOF condition, similar to the 3-DOF condition, was based on the dimensional symmetry of McMahon's FIFA framework. But this condition allowed for interaction in 6 degrees of freedom. 3 axes for position and 3 axes for rotation. The medium-fidelity large-screen immersive display no-gravity condition utilizes a head-tracked large-screen immersive display along with 6 degrees of freedom interactions. Collision physics was improved in this condition and gravity was disabled to try and mitigate some of the usability issues. The medium-fidelity large-screen immersive display gravity condition is similar to the lower-fidelity conditions, but has a gravity vector pointing down relative to the user instead of directly into the screen. This condition mimics the real-world interaction more accurately and was expected to be more familiar to users. The high-fidelity head-mounted display no-gravity condition uses a head-mounted display instead of a large-screen display, allowing virtual end effectors to be co-located with the physical hands. The HMD conditions helped reduce visual motor offset between the end effectors and the display. Gravity was disabled in this condition. The high-fidelity head-mounted display gravity condition was the highest fidelity condition with gravity being enabled. Users could move around like they would in the real world and move up close to the objects to get a better view. Biomechanical and transfer function symmetries were also improved in this condition. The independent variables were time and condition. The questions on the pre- and post-questionnaires were analyzed using the Bloom's taxonomy. The dependent performance variables like number of attempts, time to complete, answer difference, etc. were recorded during the simulation across all conditions. For the results, please see our paper evaluating multiple levels of an interaction fidelity continuum on performance and learning in near-field training simulations. Thank you.